I did it. I did it. Can you guys hear me?
Yes, we can. Well,
Okay.
I can.
I can.
Sweet. Good. Give me just a second, all. I'm trying to simultaneously print a copy of the practice test in case there are questions that you guys want to go over. Come on. Nothing can ever work right. Nothing's working right today. Let's try this one more time, and if not, I suppose I can just write down
Well, I'm sure that you could just do a screen share and pull up the practice quiz if your printer doesn't work.
I can, but I would rather have it to write on so I can circle things on the quiz. But if it's not going to work, it's not going to work. Give me one more shot, and if not, we'll just do our best without it.
Perfect.
It's working.
Yay.
Why does everything have to be so difficult today?
It's the Mondayest Wednesday ever.
Yeah.
I feel like every day during the week right now is Monday.
Yeah.
Every day there's something that goes wrong. Groundhog Day. It's Groundhog
Right.
Day.
Okay. Now. Sweet. So since we have our exam coming up next Tuesday, I thought I would give us the chance to look at any practice test questions that you have. So the practice test is on Canvas now. It's awesome. You should definitely check it out. That way we can have the discussion about the practice test on film for a few days for people that want to review it. Have you guys checked out the practice test yet? If not, open it up and follow along and we can discuss some questions.
Do you want us to lead with the questions?
Sure, if you have some questions, then we can definitely talk about whatever you want to talk about first.
Okay.
And it doesn't have to be practice test questions. It could be homework questions. Like
I got some.
we're reviewing anything from 11 through 14 is fair game at this point.
Okay. So one of my questions is so number 3.
Okay.
We have
You're talking about
me
the
as well.
practice
Okay.
test, right?
Yes, on the practice test.
Okay.
So when I look at that, sometimes I don't know whether I need to include the lone pairs and have it be a 109.5 or not the lone pairs and have it be 180.
Yeah.
You always
So-
count the lone pairs.
Yeah, include the lone pairs because you know that oxygen has to have 2 lone pairs or else it would be a violator of the octet rule. So even though in bond line drawing, it's optional whether we put those lone pairs into the picture, they're there whether we show them or not.
Okay, so that would be, the answer would be C with that one then.
Well, let me take a look. So here I see a bond angle for a carbon with 1, 2, 3 electron groups. So that should be 120-degree bond angle. Here I see a carbon with 1, 2, 3 electron groups, another 120-degree bond angle. And here I see an oxygen with 4 electron groups. So the 1, 2 that are showing, and then the 2 lone pairs that are not being shown. So we would expect that bond angle to be 109.5 degrees. It's classic case of this is fine as a bond line drawing, but bond line drawings and Lewis structures don't always accurately represent bond angles. The only way we can tell what the bond angles are going to be is by figuring out how many electron groups there are on the central atom. So yeah, C looks pretty good to me.
And then for number 3, that would be a bent shape technically, yeah?
For the third atom, for the oxygen,
Oh yeah,
yes,
number 3,
bent.
yeah.
And for 1 and 2, those would both be trigonal planar.
I have a
Yes.
quick question about that. Does it matter about the whole, it's almost 120, but double bonds take up a little bit more space? So for instance, on question 3, that first angle would actually be a little bit less than 120 degrees because isn't the double bond above it kind of pushing down on the geometric shape a bit?
That's why it has a little.
There are a number of things at play that set this bond angle for us.
Uh-huh.
And I think it is actually exactly 120 degrees. If not, it's within 1/10 of a degree of it. But you're never going to have to guess if it's exactly or close to. As long as you know the basic bond angle, you're going to be fine.
Okay.
So 3 electron groups, something around 120 is your answer, right?
Yeah.
For number 4, I was just wondering, so for the functional groups and everything, you're still counting benzene rings because they're technically fair game at that point, or is
Yeah,
it gonna
benzene ring is a functional group just like an alkene is a functional group.
Okay, so I got an alcohol, a benzene ring, and an amine on that.
So those 2 groups are both alcohol functional groups or hydroxyl functional groups, if you want to name them that way, is fine.
And then you have another one on the third one there.
Yep. Yep, another alcohol. Sorry, I was just reading left to right and didn't get that far yet. I have a benzene ring here. All right, you could also call that an aromatic ring as a functional group. And then this is a secondary amine functional group. It's a secondary amine because it has 1, 2 carbons attached to it.
So do you have to say it's a secondary amine,
Nope.
or
If you said it was amine, I would give you credit for that.
Okay, perfect. And so another question is for like number 6, if we say true or false, do you want us to like reiterate why we think it's true or false?
The question doesn't ask that, does it?
Well, no.
Okay.
But
There is a correct answer there. As long as you circle it or write it down, then you'll get those points.
okay.
And the correct answer is obviously false.
Hmm.
We know it's false, and the reason we know it's false is because there are 4 electron groups on that oxygen. Even though those 2 lone pairs aren't shown, we know they're there, which makes the bond angle 109.5 and the shape bent, not linear.
And then 5 would also be false, correct?
Correct. So
Okay.
that's actually kind of a hard one. If we draw out what CH2F2 looks like,
Oh.
we could draw it a bunch of different ways, but in the end, 2 of our fluorines are going to occupy 2 of the 4 electron groups around carbon. I'm not even going to draw the lone pairs on fluorine because it's not relevant to our discussion here. but the only two bond dipoles are one pointing from carbon toward that fluorine and another pointing from carbon toward that fluorine. So if we look, they do point in a net direction. The net dipole of this molecule points out toward the side with the fluorines, which means that this side of the molecule is slightly negative and the side with the hydrogens is slightly positive. So it's polar.
So wouldn't with that, wouldn't it be anything that has like an F, an O, Cl, or an N,
Polar.
I think, would
Yep.
all be polar because it doesn't like
The bond dipoles aren't the same size. So the carbon oxygen bond is less polarized than the carbon fluorine bond is, because fluorine's more electronegative than oxygen, for example.
Okay.
So if I had CF4, then that would be a nonpolar molecule.
Because they're all canceling each other out, right?
Exactly. Those two bond dipoles are going to point this direction, and those two bond dipoles are going to point that direction. So in the end, these two cancel out with those two, and you end up with something nonpolar.
Okay. So for number 12, it's asking if it's the same compound. Are you asking like if it has the same formula? Because it does have the same formula.
No, I'm not. I'm asking, are they identical to one another?
Well, that's a tricky trick because no, they're
Not
not.
tricky.
It is because they have the same formula, but they're just different.
They're actually identical to one another.
Nuh-uh.
They're identical
Wait.
to one another.
What do you mean they were identical?
They are the exact same molecule as one another.
That's what I was
That's
looking at earlier, is because you can move that
If
CH2.
you don't believe me, Orlina, I would challenge you to this thought experiment.
No, I'm not
No, just
saying
listen. Just listen for a second. I'm giving you a piece of wisdom. All right, just take it. Give the IUPAC name for the one on the left, please. And then after that, give me the IUPAC name for the one on the right. So that's everybody that's in here right now. Practice. Write down the IUPAC name for the one on the left and the IUPAC name for the one on the right. I think what you will find is they have the exact same IUPAC name. And if they're the same name, they're the same compound as one another.
Nuh-uh. Because this one has 7 carbons on the right.
so does the first one. Count the longest chain. I just figured it out.
Oh, that's rude.
I counted it as the same formula, so that's why I said it was true, because they're each C10H22s.
Same formula does not mean identical. That does not mean the same compound.
Mm.
You can have stereo isomers and stuff.
And you could have constitutional isomers.
Yeah.
So,
And handed isomers, which I guess are stereo isomers.
right. So, sorry. This and this have the exact same chemical formula. That would be C3H6O. They are not identical to one another. One of them has an aldehyde functional group, one has a ketone functional group. They are constitutional isomers of one another. They are not the same compound.
So that was 12.
And the name is actually, I think it's 2,2,4-trimethylheptane.
Yep. For both of them, because they're the same molecule.
Yeah.
Now in space, this one is flipped over like a pancake from how this one is. So we start the numbering of this one from the left-hand side and the numbering of this one from the right-hand side.
Well, don't we start it down at the bottom with the CH2, CH3?
Well,
that-
left-hand side, yeah.
Yeah, it's tricky. That's tricky.
It's supposed to be, that's why it's on the practice test.
How would those ones be different if it was a mirrored compound instead of the exact same one?
Are you talking about number 12?
Yeah.
They don't have mirror images. There are no places where that molecule can have mirror images. In order for the, don't worry about that. So actually there is one place where we could have mirror images here, and it's at this carbon right there. There's a possibility for 2 different stereoisomers of this compound. But I wrote this problem this way, ignoring that possibility because it's not something that you guys have to worry about.
So when you're asking for that same, I'm just like thinking about the words and the way that things flow. So when you're asking if it's the same compound or whatever, like,
Are they identical to one another? And if you're not sure if they're identical, because obviously this one was pretty tricky, right? Name it. Name each of the pair of them. If they have the same exact name, they're the same molecule as one another. That's the whole point of having IUPAC names, is that every individual molecule gets its own unique name. So if you name two of them and they have the same name, they're identical to one another.
Okay. And then number 14, so when you're asking for the shape, like for a 6-figured one, that's a hexagon, correct?
I'm talking about any of the carbons. So you have to talk about the shape of any one of those carbons. So it doesn't matter which one.
Tetrahedral.
Yes, that's right.
Sorry.
But it says geometry. Geometry would be hexagon.
Geometry is another word that they use. That's why I put in parentheses shape, because that's another way that chemists talk about the shape around a central atom. They call it molecular geometry.
I have a question about 11.
11, all right.
A lot of them are kind of right, but I don't really know which one's right. Well, it's not a
Well,
continuous chain.
okay, so you've never seen this name before, right?
No, but I looked it up in the
Good.
book.
No, it's fine. You don't need to have seen this name before. What you have to know is how naming works. So you have seen this name before. What did the prefix pent have to do with that molecule? What does it tell us?
Number of carbons.
Right. So only one of those answers talks about a number of carbons in the chain. And that's what you're supposed to be able to figure out, is that the prefix, that part of the name, refers to the number of carbons in the longest chain.
In the
Okay.
back of the book, it also has something that's relatively close to that word that talks about 20 carbons.
Yeah, but I don't, and I looked in the book too, but it didn't say it was continuous. So I didn't know if there was, actually continuous.
There's only one answer that makes any sense out of these.
Okay.
All of these things are true about icosane, but what the prefix refers to is how, like, that's a question like, do you understand the IUPAC system for naming? That's really the underlying question there. And that
Gotcha.
prefix specifically talks about how many carbons are in the longest chain.
So I totally
Right.
skipped.
You don't have to know that prefix to know what it means. That's the, if I said pentane has the structure blah, 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 what does the prefix penta specifically indicate? Then it's like too familiar. So it doesn't get to the root of whether you really understand the system of naming. If you understand the system, even if there's a part of the name that's unfamiliar, you know what it's referring to at least.
Right.
So I totally skipped over 13 when I went over this earlier. But oxidation, isn't that where you add oxygen to a compound?
Well, that's one of the ways that we can oxidize. So generally speaking, when we're talking about oxidation in organic chemistry, we're talking about adding more carbon-oxygen bonds or adding more carbon-carbon bonds sometimes. But almost always, we're talking about decreasing the number of carbon-hydrogen bonds. That's
Okay.
oxidation. So that makes this false, right?
Yeah,
So we
well,
don't
what I
wanna get
remember
more
from
carbon-hydrogen bonds, that is actually reduction, not oxidation.
what I remember from Chem 121 when I did take it was when you're oxidizing, you're adding oxygen because you're adding O.
That's
And-
one way, but it's not the only way to oxidize.
Right. But from that question, like, that's what went through my head.
So the notion that we have for Chem 131 in terms of defining oxidation and reduction is sort of simplistic. And the reason why is because we don't take the time to talk about how to evaluate the oxidation number of a carbon or of any other atom in a Lewis structure. And it's because it's kind of a complex notion. It's best left to majors level chemistry classes. So
Isn't it-
instead we do the sort of shorthand version, which is Normally oxidation means we're getting rid of carbon-hydrogen bonds and adding some other kind of bonds instead. Most commonly carbon-oxygen bonds, but it's not the only kind. Ariana, you look confused. What did I do? What did I say?
Oxidation reduction, doesn't that have a lot to do with the electrons
Absolutely.
during a formula and how the electrons are exchanged? That's the oxidation reduction, isn't it? Kind of.
Yes and no. So oxidation reduction isn't always a full exchange of electrons. Sometimes it's exchanging bonds that are polarized one way for bonds that are polarized the opposite way. So we can talk about a carbon being oxidized when it's not giving away really any electrons. It's just bonding to something that ends up more electronegative than what it was bonding to before. So there's no electrons really changing places there, but bond polarities change. And that's very often the way that we have to define oxidation in organic chemistry.
It's the energy level of the molecule's bonds that's changing, right? Like
So-
when you're considering activation energy, it has to do for the molecule, not just specific. Well, I guess it comes down to the bonds, basically. You're changing the energy level of those bonds because you're increasing the bonds. Right?
It's not really energy level of bonds. At least that's not how I would talk about it. So let's just look at a really quick example of an oxidation reduction reaction. This also happens to be one of the two reactions of alkanes that I expect you to remember, which is combustion. So this is unbalanced right now. I got to balance it. Looks like we need 2 of those and 2 of those. So if I'm trying to track what is happening to carbon in this reaction, it starts out bonded to 4 hydrogens and ends up with double bonds to 2 oxygens. All right. So I'll give you the sneak peek for how we would figure out the oxidation number, which is not quite the same thing as charge, the oxidation number of these carbons. So if you ever want to figure out what the oxidation number of any element is in a Lewis structure, here's how I teach to do it. All right, this is not something that you have to do. There's a reason why I don't go through this with the class, because it's confusing to a lot of people and only helpful for a few. But Ariana, this might help you. All right, so
Thank you.
you're welcome. So when I teach oxidation reduction at the majors chemistry level, when I look at that carbon and I want to find its oxidation number, this is basically just a way of keeping track of whether that atom is becoming more partially positive or more partially negative over the course of the reaction.
Okay.
Here's how I do it. I take its number of valence electrons and I subtract the number of electrons it is holding based on electronegativity. So let me explain what I mean by that. So you won't probably find this exact formula in any textbook, but basically when we're talking about oxidation numbers, we're going to look at every bond carbon is sharing.
Mm-hmm.
And we're going to determine whether carbon or the other atom is the more electronegative atom. And we're going to assume that whichever atom is more electronegative is the one that's holding that pair of electrons. So in this case, carbon has 4 valence electrons, and we're going to subtract 2, 4, 6, 8 electrons because carbon is more electronegative than hydrogen is. So it's holding all 4 of those pairs of electrons it's sharing. So basically we have to assign every pair of electrons to one atom when we're talking about oxidation number.
Kind of like an ionic compound.
Yes, except we know that that's not an ionic compound. Okay,
Exactly.
we just have to assign this pair of electrons to one atom or the other. Now, it's theoretical, right? It's just a bookkeeping thing.
Yeah.
So for this carbon, since oxygen is more electronegative, we say that that oxygen holds both those pairs of electrons. That oxygen holds both those pairs of electrons, which means carbon is holding 0 electrons at the end of this reaction. So carbon starts out at an oxidation number of -4 and ends up at an oxidation number of +4. So carbon is getting more positive in oxidation number over the course of the reaction. So carbon is oxidized. Now, what does that mean practically speaking? We got rid of some carbon-hydrogen bonds. We picked up some carbon-oxygen bonds instead. All right. Now, that's not the only way for oxidation to happen. Let me show you an example. This is an example that we've already seen. What about the oxidation of a thiol into a disulfide?
This is the hair straightening concept.
Yeah. Yeah.
Okay.
So this is how we would set the hair in place at the end of the reaction, when we'd reoxidize those disulfide bonds. So that's not cysteine, but it's another thiol. So at the
Yeah,
end of this
just resin.
reaction, don't worry about equation balancing here. Those two extra hydrogens are going someplace. You just don't have to know where.
Gas.
Well, it's not H2 gas. Don't worry. Like, that's why I said don't worry about it.
I won't.
Organic chemists don't like balancing chemical equations because sometimes things go away to water. Sometimes water adds protons. So hydrogens come and go in organic chemistry lots of times. We don't worry about them very much. All right. What I
Equilibrium.
want you to do is I want you to try and figure out what the oxidation number of that sulfur is at the beginning of the reaction. And then assume that that is the sulfur atom at the end of the reaction. You'll find that that sulfur is being oxidized in this reaction. All right. Assume that sulfur is more electronegative than carbon, and it's more electronegative than hydrogen also. So sulfur has 6 valence electrons.
Yeah.
We take away the 2, 4 electrons that it's holding all to itself, and then also the 2, 4 electrons that it is sharing with things that are less electronegative. So at the beginning of this reaction, sulfur has an oxidation number of -2. At the end of the reaction, here's where things get interesting because we have a bond between a sulfur and another sulfur. They're exactly the same in electronegativity. All right. So 6 valence electrons still. We're going to take away the 2, 4, 6 electrons that sulfur is holding here. But what about that sulfur-sulfur bond? If they're equal in electronegativity, we're going to split them.
Yeah. Got it. That's where it comes in.
Yeah. So sulfur in this case is oxidized. All right. And in this case, we're not really getting rid of carbon-hydrogen bonds and we're not really adding carbon-oxygen bonds, but still there's an oxidation reaction happening to this molecule. All right.
So the way that I learned it was when you reduce something, you're increasing the electrons that it's holding because you're reducing its overall charge. So whatever.
Yeah, but that only works with ionic compounds. There's no change in charges here at all. That is neutral. Both those things don't have a charge. This doesn't have a charge either. So when we talk about oxidation numbers for covalent compounds, we can't talk about it in terms of a change in charge because that's not. Instead, the related concept is oxidation number, which is a little bit more muddy than charges. All right.
So different terminology, but kind of the same.
It is kind of the same thing. So it's not that this thing has lost an electron over the course of the reaction. It's just become more partially positive because it's bonded to something different now.
And so something else is hypothetically more.
Something else is definitely more negative.
So that other thing is the thing that's been reduced, which therefore to be reduced, this then had to be the oxidized.
Yes, that's right.
Okay. That makes sense. Thank you.
Yeah.
Tangent.
But it's really important because for a lot of students, like this idea of I'm getting rid of carbon-hydrogen bonds and adding carbon-oxygen bonds, it's sort of an unsatisfactory idea. And that's because there's really no hard theory that says that's true. It just happens to be true that that's how oxidation works in lots of organic molecules. Obviously not in all of them because I just showed you an example of an oxidation where neither of those things was really true. All right. So in general, we get rid of bonds to hydrogen when we oxidize, and we add some other kind of bond in their place. And then the reverse is true. We add more bonds to hydrogens if we're reducing things.
Okay.
Other questions from the practice test? There were a lot of really good ones on here. I spent a crap load of time writing this stupid thing.
So for number 18,
Okay.
it says draw an alkene in a cis configuration. Do we have to add like extra stuff to it, or can like I drew
Do
mine?
you?
I drew mine
I
like
can't see. Yeah, that's what I would draw.
okay, perfect. That's what I was wondering. Do I
Or
have
if
that?
you want, I mean, this is what
to it.
Alina had if you couldn't see it. That is the simplest cis alkene that exists.
That's what I have.
You could also have something crazy like this. So
No.
there is a cis alkene functional group in there, among other things. As long as I see a cis alkene in there someplace, then you're golden. All right.
Okay, that's
If
what
you
just
want
what I
to
was
go
wondering.
simple, then that's what I would do. That's exactly the molecule I had in mind. I would expect most people to write, but it's not the only one, obviously.
And then for number 22,
Okay.
it had me going for a while. I was like, I don't think this is possible. So
Oh, it's possible. There's a bunch, actually.
figured it out. I think I have 3, but
So
I mean,
first of all, C4H6. If it was an alkane, how many hydrogens would you expect there to be in a 4-carbon alkane? Like straight chain alkane.
be 10.
10, right?
Yeah.
So if it only has 6, that means that it must have either 2 double bonds or a triple bond or a ring and a double bond or 2 rings. So it's short 2 sets of hydrogens. So for every 2 hydrogens that we decrease, we're either making a carbon-carbon bond or we're making a ring, something like that. All right.
Do these look all right?
So let me just draw some. I can barely see, but
I
that
think
seems like it works just fine.
Yeah, that's the one I have.
So count your hydrogens here. All right. There are 2 hydrogens on that carbon.
Yeah.
There are 2 hydrogens on that carbon.
Yeah.
There are 0 hydrogens on that carbon. There are 2 hydrogens on that carbon. All right.
Yeah.
You only have to draw 3 of them. They're actually a lot more than that.
And then I have a square.
So what about that?
Yeah, that works. Okay.
So I said no 2 should have identical functional groups.
Yeah.
Okay, well in that case, this is an alkene and that's an alkene, so that's not an allowed answer for me.
You can't have 2 alkenes?
No, it says no 2 can have identical functional groups. So what else are we going to do, Orlina?
Oh
We
my
have
God.
to expand our thinking a little bit.
I struggled with the third one too because I got a double bond, 2 double bonds, and then a triple bond, and then I didn't have
I
a third.
gotcha. Hold on just a second. All right.
I was
So-
wondering.
4 carbons, 6 hydrogens, right? There's 1 hydrogen there, no hydrogens there, 2 hydrogens there, and 3 hydrogens there. So 6 hydrogens total. All right. So we have an alkene and an alkyne. What else can we do with just 4 carbons? What about this? You ready for this?
Come on now.
Come
We
on.
didn't learn anything about that. What?
What's wrong with that? There are
And
2 rings in that molecule.
We didn't learn that. That's what's wrong with that.
So it's
We
like
didn't, what do you mean we didn't learn that?
When
We-
did we go over that?
So it's like 2 benzene rings that are linked together, but instead of a benzene ring, it's just 2 propyls.
Yeah. That exists. It is very unstable, but it exists. So anyway, if this was worth 2 points, you get 1 of the 2 points for just getting 1 of these 3. And then it's actually supposed to be a really hard question. This is the one that's hard to come up with.
That's
Thinking outside the box, no pun intended.
Really thinking outside the box. Okay. That's
I
ridiculous.
have questions on the homework but if people want to keep working on this, can listen.
We can do some homework questions too, but if people have more questions on the exam, let's get all that on film in one place first.
I
Is that
do
okay,
have
Emma?
questions about
Yeah.
the exam. So number 24, I just want to make sure that I thought of this correctly, because this one actually was relatively like it spun me for a minute.
Number
But
24. So first of all,
because it's attached to two other carbons, it's a secondary alcohol.
that is a secondary alcohol.
It can only be transformed into oh gosh, dang it, I just had it.
What do we call that functional group?
Yeah, that's what I have.
It's a ketone.
Ketone. Why couldn't I remember that right now?
So this is actually a pretty hard one. I think that we talked about dehydration of alcohols, which is like removing water to make an alkene. That's the reaction here, but this is a really hard one. All right. So let me give you the correct product here and talk about why. Remember that when we do H2SO4 in heat to an alcohol and we dehydrate it, we're taking an OH from one carbon and a hydrogen from a carbon next door, and then we're recreating a double bond between them. So here is the correct or a correct answer for this question.
Yes.
The hard part is a lot of people want to make that double bond here because when we form the double bond, we want our double bond to be as substituted as possible. All right, call that Zaitsev's rule. So I went over that in the topical videos. The problem is we have to have a hydrogen there in order to do our elimination, and there isn't a hydrogen at that carbon. So
Well, then with that is it would eliminate one of the other carbons there as well.
What's that?
It would also eliminate one of the other three legs.
Right. Either that or we create a carbon with 5 bonds. Any one of those things is a really bad option. So that's why it doesn't happen.
That's what I was looking at earlier. Like that one also threw me through a pretty good loop.
Yeah.
Yeah, and then do you just want the organic portion of it, or do you want also the plus the H2O at the end?
Well, it does say draw the correct organic product.
If you did put H2 plus H2O.
I wouldn't care. Yep,
Okay.
that's fine.
And then we went over the dipole situation.
That's what you mean by organic chemists don't balance the equations.
Yep. So if we were balancing this equation, then PCC would be one of the reactants. And really that's a mess because PCC is an oxidizing agent that gets reduced as it's oxidizing this, but it gets reduced in steps. And like we would end up with multiple different reduced products of PCC from this reaction. It's not the important part because we're just going to get rid of that stuff by purification anyway. That's not what we're trying to get out of this reaction. We're trying to get the product after we oxidize this thing, which by the way is
the net equation.
Well, we're just focusing on the organic part because that's the part that we're actually trying to purify and isolate at the end. So PCC takes primary alcohols and turns them into aldehydes. If you drew your aldehyde like this without showing that hydrogen attached, that's perfectly fine as well. I just like to show the hydrogen because it is part of the aldehyde functional group.
And then for 28, that other one would be, I don't remember my functional groups right now.
If you were,
that one would be a carboxylic acid at the end, correct?
Yep. And fair warning, this is sort of like something else would happen to this molecule that you guys don't have to know about. So this is the product that I'm looking for, but in reality, there's something special about those carbons, one carbon out from a benzene ring, and there's something more that can happen to this molecule when we treat it with a strong oxidizing agent, but you don't have to worry about that. This is what I was going for here.
And for number 30, are you looking for like the definition in which you said in one of your videos or like the definition in the back of the book?
Well, they mean the same thing.
Okay,
I'm looking for whatever definition is a correct definition of stereoisomers, which is
fill
a
space.
pair of molecules that have the same order of connection. In other words, their atoms are connected in the same order, but they're oriented differently from one another in space. They take up space differently from one another. That's
So
a pair of stereoisomers.
I put fill space different than each other.
Great.
All right.
But you also have to, or you also have to have the part about having the same order of attachment of atoms, because we could have very, very different compounds. This compound and methane,
Mhm.
those fill space very differently from one another, but that doesn't make them a pair of stereoisomers. So they have to have the exact same order of connection of the atoms, but take up space differently. And as a matter of fact, this one does have a stereoisomer, because that is a trans alkene right there. We could draw the cis version of that compound, and it would be a stereoisomer of this.
So then writing the one from the back of the book would be isomers that differ only in their three-dimensional arrangement of atoms.
There you go. So they differ only in their three-dimensional arrangement of atoms.
Okay.
That's another way of saying the same thing, because we're assuming that they don't differ in the way that, in the order in which the atoms are connected.
Perfect.
Yeah.
And there's only 4 in 31, correct?
Yeah.
Okay.
That one, that one, that one, and that one. I'm not going to name them. You can look them up.
If we were naming the functional groups on the actual exam, would you expect us to say it's a transalkene, not just an alkene?
Alkene would be fine.
Okay.
If you said transalkene, I would be like, well, aren't you special? And then, of course, you get credit for that. Yeah.
Gold
Yeah, it's
star.
great. No, it's great.
And 32, and that one's quite a long bit one, but
It's really not that long. It just has a lot of writing in it, because I wanted to sort of show you guys the power of organic chemistry to transform very simple molecules into much more complex ones.
mhm.
And you don't know all of these reactions yet, but you know most of them, which is awesome. So, all we're looking for is the reagents that we need to turn this into this.
Mhm.
And then the reagent that we need to turn this into this, or
Mhm.
that into that. So there are 4 different steps that you guys have to fill in. And what you need to do is look at the reactant and the product and figure out which reagent do you know about that can take this and turn it into this. And you know all of these already.
And that's
So
all the questions I have for that.
what reaction is this? Reaction A. What are we doing? We're trying to add a chlorine atom to what?
Alkene.
Alkane.
An alkane, yes. So in order to add a chlorine atom to an alkane, the only way to do that is with Cl2 and light together. That's the reaction that will add that chlorine atom to our alkane.
Wouldn't that be HCl though? 'Cause
No,
there's
a-
Marlena, HCl is how we add hydrogen and a chlorine across a carbon-carbon double bond.
Yeah.
That's a reaction of alkenes. So here we are taking a carbon-carbon double bond and adding an OH group to one side and a hydrogen to the other. So that is acid catalyzed hydration. So we have to use water and some kind of acid, the most common acid, H2SO4.
Do you want us to also have like the part on the bottom? Or if we just put like the Cl2 or the H2O or whichever, would
If you
that
just hit Cl2 and light on the, it doesn't matter what goes on the top and the bottom, but you have to have light, or heat is also used sometimes, but that's really dumb. That's not the way
Okay.
organic chemists do it most of the time. Your book says light or heat, so I'll accept either one, but I don't like heat very much for that reaction.
Photon energy.
Light energy is better. So the energy has a specific purpose, and the purpose is to split up those Cl2s into chlorine radicals, because this reaction works through a radical mechanism. So anyway, the light works a lot better to do that than heat does. So what are we doing here? We're starting out with a secondary alcohol. We're ending up with a ketone. Well, how do we do that? There are actually two reagents, you know, that can do that. Actually, three, if you paid really close attention, because I said that Jones reagent could be K2CR207 or H2CR04. So either of those, Jones reagent, you could just say Jones reagent, and that's fine. Organic chemists have huge egos, even in published work. Sometimes instead of writing the structure of a reagent, they'll just give the like name of the dude that invented it. All right.
So
So
just
the
giving one,
Grignard reagent, that's instead of drawing out the structure of the reagent, that's a Grignard reagent, by the way, right there.
so just giving one of the three, or
Yeah, any one of them. All I'm looking for is a way to turn this into this. So if you said PCC, PCC wouldn't work if it was a primary alcohol to turn it into a carboxylic acid, but it turns secondary alcohols into ketones just fine. Just the same way Jones reagent would do this reaction. All right, so I'm just looking for a set of conditions, a reagent or set of reagents, like so water and H2SO4 are both required to do that acid catalyzed hydration. Just tell me a way to turn this into this. So in this case, Orlina, how are we going to turn that alkene into the dibromide?
you're going to add Br2 in a metal, I believe.
You don't need the metal,
You don't need the metal.
Here too.
just Br2. So if we were talking about adding hydrogens to each one of these two carbons, H2 is the reaction that needs the transition metal catalyst along with it.
Yeah.
Nickel.
And we just filled in what we refer to in organic chemistry as a total synthesis. So very simply, we turned that 4-carbon alkane into a much larger and more complex dibromide. Interesting. So that's what I'm going for there when I wrote this question, was just to show you that like there's a reason that organic chemists learn these reactions, because in the end, it allows us to take really cheap, not complex starting materials and make really interesting stuff out of them. That's why we spend all of our time learning those reactions. And you guys know a bunch of them already. Okay, Emma, homework questions. What you got for me? Oh, Emma, you're talking and you're muted. I can't hear you. I was just waiting. I thought that you were like getting your stuff together.
No. Hi. So 1461.
Okay.
And like checking my answer in the back of the book, it has a major product and then another product. And
Don't worry
I'm
about
a little,
the minor product.
okay.
Don't worry about
Because
it.
we didn't really learn how to do that, so it doesn't really matter, right?
Yeah, it doesn't really matter.
Okay. At this point. Of course it matters.
It really doesn't. Oh, that's too many carbons.
Right, what are we looking at here?
So if we do acid catalyzed dehydration of these alcohols to make alkenes, what is the major product that forms? Now, the cool thing is we know that we're going to take an OH from one carbon and a hydrogen from a carbon next door to recreate a carbon-carbon double bond. All right. So In this case, it doesn't matter whether we pull our hydrogen from here or here. We're going to end up with the same product anyway. So that that delta sign is just to represent heat. That's like a shorthand. So H2SO4 and heat would give us that product.
Okay.
And it doesn't matter where that double bond really lies at because they're all the same.
Product, right?
Yeah.
Name it. If I had drawn it like this, would it be any different? I did this just to get under your skin, Orlina. I did that just for you. So
actually, it was actually pretty close to what I had, but it didn't say it in the back of the book. But I was like, they're exactly the same. So
they're the exact same thing. And if you don't believe that, name them. So in each case, what would we call those?
Cyclo pentene.
The 116. You had to.
Pent is 5. There's only 4 carbons in that ring. So that's cyclobutene.
Butene, yeah.
All right. And it doesn't matter which one of those you're talking about. It's still cyclobutene. So if they have the same name, they're the same molecule. Yeah. It doesn't matter where we show that double bond, even though we know that it's happening because of a hydrogen being lost either here or here, and then the OH group being lost there.
Sure.
So in this case, we do have options because we could steal our hydrogen to do the dehydration from this carbon or from this carbon. So in that case, we have to use Zaitsev's rule. And Zaitsev's rule tells us that the alkene that forms in a dehydration reaction, so this is a type of a reaction called an elimination. So the alkene that's formed in an elimination reaction normally is the one that has the most carbons attached, the most substituted alkene. So that means that we're going to eliminate by taking one of these hydrogens, which means our product would look like this. Note that I've drawn the trans isomer here. If you drew the cis isomer, that's also a possibility for the product, and that's fine. All right, for very similar reasons, when we do H2SO4 and heat on this molecule, we end up with this as our correct product. If you drew the double bond here instead of here, it's the same molecule one way or the other. If you don't believe me, name it.
Right.
And actually, there is a possibility for cis and trans isomerism with this molecule, but don't worry about that because this is a methyl group and that's a methyl group. So these two methyl groups could be on the same side or on opposite sides of that double bond, but don't worry about that. And then finally, oh, whoops, arrow's the wrong direction. If we treated this thing with H2SO4 and heat, there's only one carbon next door to that OH group that has any hydrogens. It's this one. This carbon doesn't have any hydrogens. If we try and draw another bond there, that would be a 5th bond to that carbon. That's a no-no.
That makes sense. Because there's a question similar to that on the homework. And that makes sense why I put it down wrong.
Yeah. So this, it could be cis or trans, but the alkene has to be between those two carbons. Generally speaking, elimination reactions, we make the trans product in greater yield than the cis product. In reality, it's actually a mixture of the two of them, which is sort of like, sometimes it doesn't really matter whether you make the cis or the trans alkene. Depends on what you're going to do with it later. Emma, any more homework questions? Was that helpful?
Yes, it was. Yes, I was. My other question is 71.
Okay.
So basically, what are you doing with that?
Yeah, hold on a second. Let me draw it out.
Yeah. Do I want to Also, if I have to leave, I'm not trying to be rude. I'm just baking bread and need to get it out of the oven.
Sweet. I like bread.
I've been baking a bunch.
Okay. What oxidation product is formed when we create cortisol, this big thing, with K2CR207, so the Jones reagent? So what does K2CR207 do? It turns primary alcohols into carboxylic acids. It turns secondary alcohols into ketones. It doesn't do anything to tertiary alcohols. In order to
Right.
oxidize an alcohol, you have to have at least one hydrogen at that carbon where the OH group is attached. So with that being said, that is really what this question is asking, because cortisol happens to have all three kinds of hydroxyl groups in it. It has a primary alcohol, a secondary alcohol, and a tertiary alcohol.
Secondary. And tertiary.
So the first alcohol that we get to is that alcohol right there. That is a secondary alcohol because that carbon is bound to 2 other carbons. So secondary alcohols are oxidized to ketones by K2CR207. Tertiary alcohols are not affected by K2CR207. Primary alcohols, like that one, are oxidized to carboxylic acids.
Is it bad? So like when it gets up, so obviously the benzene ring's not, but when I get up into the far right corner of that, sometimes I just decide to start putting in C's instead of just doing like bond line drawings. Is that bad?
So even in the book, they have these methyl groups replaced with CH3s.
Okay.
Just keep your carbons straight. All right.
Okay.
If you have some condensed form in there and it's still correct, that's fine. I don't care. I can read it one way or the other. It's just a
Okay.
language, right? So I just
Right.
choose online drawing because it's faster to draw.
Yeah.
So on that, yours is kind of flipped a little backwards than what they have in the book.
Backwards. Do you mean that?
Yeah, so the double bond to the oxygen is at the top, and the COH is where your double bond to your oxygen is.
So
I
no
was
big
just
deal. It's the
okay.
same molecule because remember that carbon-carbon single bonds can freely rotate. We could
Mhm.
just rotate around that carbon-carbon bond right there and
Mhm.
flip the positions of those two things and it wouldn't change anything at all.
Okay. I think it just confused me because it was like the way that they have it written out, it's actually COH. There's no like line to the OH portion of it. So I think that's what.
Oh, they did it like this?
Yeah.
I mean, that's fine. It's sort of a condensed structure thing instead of bond line drawing, but that's fine.
Okay.
That's a college.
Yeah, I like that question. That's a really fun question because it forces you to think about all different types of alcohols and how they behave in the presence of oxidizing agents. So I think that's a fun question, which is why I included it on the homework.
So I have a question about 69B.
Okay.
So the way that the answer is, I mean, it kind of makes sense, but at the same time, it doesn't. So the way that they have it, it's CH3, CH2 in parentheses with a 2. So wouldn't that mean that it's connected to the single carbon right there? But wouldn't it be up or down instead of to the other side of it?
Oh, wait, 60 what now? 69?
69B.
So there is the bond line drawing for 69B's starting material. Because we have two CH3 CH2s attached to that CH with the OH.
I get that bond lines are easier for you at this time, but can we try and do it like what the book has? Because
so what I'm telling you is if you can't see where the OH group is, draw the bond line drawing first. And if you can't draw the bond line drawing, then let's talk about it and see how you can get there. All right. So if we just start by drawing this part of the molecule, that is a carbon with one hydrogen and an OH attached. Are we good on that so far? So just that part, that piece. And to that carbon, there are two ethyl groups attached. So let's draw those in.
I guess where it confused me was like, I was looking at it as like a tertiary where like at the top you'd have the methyl group and then at the like.
Here's how you know it's not a tertiary alcohol. That carbon has a hydrogen attached to it. So you can see right in the condensed structure that hydrogen belongs to that same carbon as the OH group. So you know it can't be a tertiary alcohol because that carbon that is holding the OH group is also holding a hydrogen. But seriously, probably on an exam, I would give you this instead of this. But if I gave you this and you couldn't see what the structure was with it written as a condensed structure, draw it out as a bond line drawing first. That sounded like pinball. But I guess it's probably bread ready to come out of the oven.
Okay.
So in the end, we know that K2 or K2CR207 oxidizes secondary alcohols to ketones. So there's your.
I guess what it was just confusing me, as I said, because the way that I was looking at it was, I'll write it out really quick. So that was the way that like my brain figured it out to be. But then now looking at it, because you have the CH3, like.
So that looked fine other than the fact that I couldn't tell where your carbon was being attached away from where the carbon with the hydroxyl group was. So you just put a bond in kind of a careless looking place. So that bond that's going straight up, it looks like it's going to a pair of hydrogens. That's weird. Does that make sense?
Not really, but I'll figure it out.
Hold on. So this is very similar to what I think I saw you draw. The only difference is I am showing this carbon-carbon bond going from a carbon to another carbon. Your bond sort of went up to these two hydrogens, which doesn't make any sense at all.
Well, that's the way that I just did it really quick. I know that they're supposed to go to the carbon-carbon, but
I'm just saying, don't be careless in your position of covalent bonds. That's important.
Yeah.
Okay. So still, you can see on this carbon, even though this is more of a condensed structure than a bond line drawing, you can see that's a secondary carbon or a secondary alcohol, because that carbon is bound to 1, 2 carbon-based groups, right?
Yeah.
So the carbon containing the hydroxyl group is bound to 1, 2 carbon-based groups. So it's a secondary.
I was able to reduce, or not reduce it, but I was able to figure out the reaction. I was just having an issue of like writing it out how the book has it, because they don't have it in bond lines so much. They just have it in like the carbon hydrogen reduced form. And so it just didn't make a lot of sense in the way I was trying to connect it.
So you could also draw the book might have given the answer like this instead. That's also a perfectly acceptable answer.
No, it gave it to us like this.
Which is the same thing. It's just not in the same kind of.
It's a different order, and so I guess that's just where I'm getting caught up.
Yep. So in the end, if that doesn't make sense to you, try and draw bond line drawings of everything and see if it ends up being the same thing or not. All right. Sometimes, like it's very hard in organic chemistry to know if two things are identical, because things can be twisted. The way that we draw the bonds can be very different. So even with something as simple as pentane, those look very different from one another, but they're the exact same thing. All we've done is rotate some carbon-carbon bonds, and that's the struggle here. Like, this is exactly the same thing as this, but they just don't look very, sorry. This is exactly the same thing as this. They just don't look very similar because different ways of drawing out the same thing. So if I was you, I would try and draw both your reactant and product. If you're trying to compare it to what the book says, draw them in a way that is the easiest to interpret for you. For me, it's bond line drawings. So if you draw the bond line drawing of that, what the answer in the back of the book, it looks just like this, right?
Yeah.
Even though this would also be the exact same thing, because all we're doing is rotating around a couple of carbon-carbon bonds. So if you get really stuck, like, is my answer the same as the books? Name it. Name whatever the product is, and name what your product is. If they have the same name, they're the same thing. That's our ultimate, like, nuclear option for trying to decide if two molecules are the same or not. Name them. If they're the same in name, they're the same molecule.
All right.
Any more questions? Sweet, we got to cover a lot of the practice test. That was fun. Ariana, you got a question?
Anyone. For diols,
Yep.
The book mentioned that they're called glycol or glycerins.
Don't worry about it.
Okay.
Yeah, those are common names. Don't worry about that.
Are there such a thing as like a trial? And excuse me, there are trials. Do trials have common names, just like diols have the common name of glycol?
Glycols. I actually don't know if trials specifically have a common name or not.
Okay. Short question.
I'll tell you, it wouldn't surprise me if they did. That should also tell you how much I care about naming in general. Now, a small amount of naming is really important for all of us to know, just to, like, when I say, what does that ketone do? If you don't know what I'm talking about, or what does butanol do when I treat, like, if you don't know what butanol is, or that all suffix, if you don't have some naming, then you're sort of in the dark. But there's such a thing as being like too fixated on naming as well. So if we try and figure out common names for every possible functional group, there are a lot of common names out there, and you can spend all your time worrying about them. Or you can just know the basics of naming, and then most of the time what we're doing is looking at bond line drawings anyway. So then the functional groups are a lot clearer.
If we have time, I have another question, but it's not really directly related to anything, I suppose.
Sure. So one triol that I know about is this glycerol. So that's a triol, but it doesn't have like a name. Glycerol's its common name. I don't know if triols in general have some sort of common name that describes them. I don't know.
Okay.
For number 65, do you just need to put like, it's asking for the alcohol needed to form each of them. In the back of the book, it shows what it's reacted to once you add like the H2O. Is that what it's looking for?
The reverse reaction.
It's asking for the starting material. So basically, like if I was drawing out 65A, I would be looking at the product of the reaction. So the product of the reaction looks like this. That's exactly what 65A structure is. It's just I drew it in bond line form because it's prettier. All right. And then we did that by doing dehydration. So we treated some alcohol with H2SO4 and heat, and they're asking, what alcohol did we treat? So in the end, one of those carbons is going to have a hydroxyl group and the other a hydrogen. It doesn't really matter which one is which in this case because it's a symmetrical compound. So something like that would work just fine.
Okay.
That's actually really fun. Oh, I haven't completely written your exam one yet. I might include like draw the starting material instead of draw the product. I haven't done any of those yet. Now I'm like, what can I do? Certainly a fair question.
Okay.
I have another small question, I think. It's a tangent
Okay.
question.
Okay.
Polyethylene glycol, or PEG.
Yep.
Would that simply be multiple triple bonded 2-carbon alcohols?
Ethylene glycol is like ethane with an OH group at each one of the 2 carbons. So if you put a bunch of those together, here's what polyethylene glycol looks like. So it just keeps on going and going and going. It's like we put a bunch of them together by connecting, by basically doing a dehydration to join 2 of the ethylene glycols together by taking an H2O out.
So is that kind of like a lipidy type thing-ish?
No, it's actually very, very polar. So
Because
if you look, all those oxygens allow this thing to hydrogen bond with water like crazy. So polyethylene glycol is very water soluble for a polymer.
Okay.
Note that polyethylene glycol, other than at the very beginning, it doesn't have a lot of hydrogens covalently bound to oxygen, which means that it doesn't really hydrogen bond very well with itself. But because of all those oxygens, it can form hydrogen bonds with water that has those hydrogen bond donors. So because of that, it's very, very water soluble because we can surround this thing very efficiently with a solvent shell of waters.
Okay.
But we didn't talk really about polymers at all. So take from that what you will. Like there's a lot to learn in this class. And that is like a trifle. It's something that you know everything you need to know to be able to learn about it. But I don't want the class to be information overload. So I try and teach you like first principles rather than trying to analytically cover every single topic that's in the chapters.
it came up in one of the podcasts I was listening to, because that's one of the components to the coronavirus vaccine is PEG, and it is in the allergy world as well. So I was interested in it, and I realized that I could kind of break down the name
Yep.
from what we've learned. But then
So
I was
the
like, I don't really
poly,
know
that's
what-
the hard part when you say poly something. The hard part that chemists have to like think about is how are those individual units put together. So ethylene glycol looks like this. Putting a bunch of those together, you can see how they're put together now when I show the structure, right? But yeah.
Okay.
yeah, there's a little gap to fill in there sometimes.
Got it. Okay. Now I see how you got to the bottom one. That's
Any
what I
other
was
questions?
if it was just a whole bunch of free floating ethylenes, or if they were attached to one another.
No, they're covalently bound. That's the whole point of a polymer is we have a bunch of monomers like this that end up covalently bound to one another somehow. So that's how we grow our polymers, by making new covalent bonds. And there are lots and lots of polymers that are really important to how we live our everyday lives. Nylon is one that we actually normally make in the Chem 131 lab. We don't get to make it this year because we're not in person, which sucks.
Got it. Cool. Thank you.
So the practice exam is not like obviously going to be exactly like it, but it's pretty close to what the exam is going to look like.
Orlina, I haven't even written the whole exam yet. So how am I going to answer that question?
I just want to know if there's going to be like any like paragraphs that we need to write.
Maybe. I'm not saying no. All right. All I'm saying is that like I've given you at least some clue as to what the format should look like, the degree of difficulty of the questions, the kinds of things that you might expect to see. All right.
Okay.
I think that's pretty good. And also you have all of the notes, all of the chapters, all of the recitation videos, like you have a ton of resources at your disposal. And you know what things I focused on in the topical videos, what things I've focused on in recitations, and you know what few things from the chapters, if you've read the chapters carefully, I've ignored a couple little things from the chapters. If I've completely ignored something, there's a lot less chance you're going to see that be a focus on an exam question.
Okay. I just don't like getting blindsided with like
How
paragraphs.
many professors do you have that write practice exams just so that you can see the kinds of questions you expect? That's pretty good, right? I didn't have to do that. I could have just been like chapters 11 through 14.
Yeah,
You have
I mean-
homework questions, right?
I've
So,
had
I mean,
some that
homework
were like
are-
the practice exam, but just kidding, because it's nothing like the test.
But really, the practice exam in a lot of ways was very similar to a lot of the homework questions too, right?
Yeah.
So these are all tools that I've used to help prepare you. And you
Okay.
should use those to help prepare yourself as you go back. And instead of just trying to think of what the right answer is, think of the principle that each question is representing and focus on those. That's how you're going to do really well in the exam.
Okay.
Because I guarantee you, we're not going to like come up with a principle out of thin air that has not been discussed already. That's not happening.
Disregard my questions.
That's-
Well, unless I say everybody don't worry about this. This is just for enrichment, right?
That's what
that's
happens is
different.
when we go on
Happy to
off
answer
a
questions.
tangent,
I'm a chemistry nerd. That's why I do what I do.
it's hard. Like when we do go on tangents and stuff, I'm like, okay, I know they said not to pay attention to this, but like,
But I don't
Well,
want to take him at
actually
face
have to-
value. I don't want to believe Dr. Musk when he tells me things.
I've had some tricky professors in my time.
Oh, and by the way, I guarantee you that there will be a bonus question on Saved by the Bell for exam 1. And the reason why is because there's a reboot of Saved by the Bell that is out there for you to watch now. So I was the biggest Saved by the Bell fan in the history of the world at one time. The show is like 30 years old at this point. So I can't really ask questions that are trivia from the original show anymore because nobody gets them right other than people that are my age or around my age.
Hey,
Which really
hey,
isn't fair. So instead, now I get to ask about Saved by the Bell because there's a brand new season of Saved by the Bell that's out now.
On what? Is it on Netflix or Hulu?
On Peacock, the streaming service for NBC. But if you have Comcast, you get Peacock for free.
I don't pay for, I just pay for internet. I don't
Well,
have.
there are also illicit ways to come by the first season of Saved by the Bell.
If you
Okay.
have time to watch it.
I can make time for an extra credit question.
It would be 1 point. It's going to be a trifle. But anyway, I like extra credit questions, just like a fun 1 point question at the end of a test. Those are always something that I enjoy writing. So I am very excited that the reboot of Saved by the Bell has given me an opportunity to have Saved by the Bell trivia questions on my exams again.
Is
Because
it like some of their kids?
when I started teaching, which I had my first general chemistry course that I was in charge of in 2001, which is unbelievable. I was a first-year grad student. It was a pilot program at University of Illinois. Back then, it hadn't been that long since the Saved by the Bell, like the Zach and Kelly years of Saved by the Bell were over with, right? So it had been very recently. So everybody remembered. I could ask trivia questions about it, and some people would get them. And then it's been like 20 years since then, and it's just not the same anymore. People don't get those questions right. So now I can ask reboot Saved by the Bell questions. And if you don't get them, it's fine. It's just 1 point anyway.
So is it like their kids are in high school now, or?
Partially, yes. Yes.
Oh,
And
okay,
some of
so
the original cast, most of the original cast was back in either as a regular for the show or at least like in some part of the first season. It's really fun. If you like Saved by the Bell, then I definitely would recommend you checking out the reboot.
I liked Saved by the Bell and Full House, so I've already watched the Fuller House.
Yeah.
Which is super great. Love it show. So I'm gonna definitely have to find a way to
yeah, if you like if you were a big fan of Saved by the Bell, the new show is definitely worth it. It's got a little different tone to it, and it's sort of fun. It touches on lots of themes of like equity and inclusion, but also sort of poking fun at woke culture at the same time. Like, it's fun. It's a really fun show.
Okay, I'll have to look into it.
It's an equal opportunity offender, I would say, like in good spirit, not in bad spirit. All right. If there's nothing else, you guys, when we meet next Monday, we will be going over chapter 16 stuff. So I'll have chapter 16 and hopefully even chapter 17 topical videos all posted for you guys. But the exam's on Tuesday. So if you don't show up for that recitation because you're busy studying for the exam, at least it'll be on video where we're starting to cover chapter 16 stuff. All right. So that's going to be next Monday.
Okay, awesome. Thank you.
Yeah. Have a good night, everybody.
You too.